Hey, this is the seventh installment of Advanced J1939. What I have here, I've drawn two controllers. So going back to the arbitration and the importance of arbitration and the fact that we can have one controller trying to drive the CAN bus into a dominant state while the other is permitting it to um, go to the recessive state. So this concept of you have to drive to the dominant state and you let the system go back to its natural state for the recessive state. So I'm going to try to explain that and show that a little better. I've got a bunch of voltmeters and ammeters. I know measuring current isn't something that a lot of people do a lot of times, and for sure you're not going to have this many ammeters in a circuit. But in order to try to explain this with the easiest way I guess I can, I put a bunch of ammeters in here. So if we look at what I have here, I have basically I have two controllers. This one I've put physical switches to allow us to drive to the dominant state. The other one we're just going to leave it in the recessive state. So I just didn't put those switches in there to simplify this. So we can look right now. The voltage differential is approximately 0 volts between CAN high and CAN low. Well, it's actually exactly 0 volts because my simulation is perfect. This is exactly 2.5 volts. This is exactly 2.5 volts. The resistors are the exact values, 25K. There's no variation any place. So if we look at what happens here, it's really kind of amazing. We can see when I have both of the switches open, so I'm not driving to the dominant state. I'm just letting the system be at the rest or the natural state, the recessive state. I have the supplies, both voltage supplies, there's no current that's flowing anywhere in this circuit. So we can see by these ammeters, we can see that the way these ammeters also work is when it's shown with the A this way, this would be the plus terminal of the ammeter, this would be the minus. Same thing over here. So this is the plus, this is the minus. So it really doesn't matter right now because they're all reading 0. So there's no current that's flowing in this circuit, which might seem kind of odd. It's like, well, I've got 2.5 volts here. But I have 0 volts that goes through the terminating resistor, or 0 volts that's dropped across the terminating resistor because both CAN high and CAN low are both held at 2.5 volts. They have to be because it's in parallel, right? This is in parallel. So if I looked at this with respect to ground, which I don't have anything here that's grounded, right? There's nothing that's grounded. This is grounded, this is grounded, this ground is open. There's no current that's flowing because there's no path anywhere for anything to get back to ground. So therefore, all these are going to do, both these 2.5 volt supplies, is just drive both CAN high and CAN low. Or I say drive. They're going to cause them to be at 2.5 volts with respect to ground. Now, if I take a meter, this is going to be amazing. We grab a voltmeter here, wherever my meters are. Someplace, here we go. So if I take a voltmeter and I put a voltmeter in place, we're going to just take a look and I'll show you something that's going to happen. We'll get another one and we'll put another one up here. And until I put some ground in here, let's go ahead and get a ground. And I put a ground here and I'm going to put a ground on the other meter. So this is like you measuring the voltage. The first thing you probably see is I now have some current flow. Well, that current flow is actually going through your meter. So when you put your meter on the bus, let's say that there's no current flow. As soon as I put my meter on there on the 9-pin connector and I measure to ground, my meter, this one, it's modeled as a whole bunch of resistance. I can't count the zeros. It looks like a gig of resistance. So that's a lot if I counted the zeros right. I think I did. I think it's a gig. So that's a lot of resistance. But still, there's just a minimal. This is nanoamps. This is 10 to the -9th. It's very small. It's got a bunch of zeros in front of it. Your meter wouldn't even measure this. You don't have a meter that's accurate enough. A Fluke 87, none of those are going to measure a nanoamp. So we could see, though, that when I do put the meter in place, I do have some current flow. So let's go ahead and get rid of the meters. I just wanted to show that these are at 2.5 volts. So we'll go ahead and get rid of those. I used to call this the Heisenberg uncertainty principle. If you know anything about that, what that basically says is once you observe it, you change it. So this is something test engineers kind of live by. It's like I've got to know that once I put my meter or some instrumentation in place, I've changed the circuit. So just be aware this is some of the reasons electricity sometimes doesn't make sense, it's because your test equipment, the equipment that you're using, is actually changing the system. So you saw that there. So this is in perfect theory how it works. If there's absolutely no path to ground any place, and this is great because everything's the exact values they're supposed to be, unlike real stuff, which varies. And, this isn't going to be exactly 2.5 volts. This would be 2.49999 or something. So yeah, it would have some current flow from this one over to this one, but because they're exactly 2.5 volts, everything here has a potential of 2.5 volts. So there's no current flow. So that may kind of throw you a little bit. Maybe look at this and draw it out, sketch it out, and see yourself. It's like there's no current that's flowing here. Everything's just being held at 2.5 volts. It wasn't until I put something in ground place or something that is grounded, such as that meter, where I could actually see some current flow. So I'm going to go ahead and close the switches. Let's go ahead and close. Let me get both of them closed here before we look at this, because we always close both at exactly the same time. So let's look at what's happening now. My meter shows a difference of, so this is the dominant state. This is this CAN transceiver driving the bus to dominant state. The other one over here is at a recessive state. And so once we drive to the dominant state, what happens is we get our voltage difference of 2.136. We consider this a logic 0. Great. What's happening is this 5-volt supply that's inside of this device, whatever this is, engine controller, transmission controller, who knows, whatever it is, this 5-volt supply, there's a FET that's switched on here. I just got it to the switch. We can see there's like 35.69 milliamps. We go through this diode. We come down to this point, and be careful here, this is 42.73 microamps. So this is about 1,000th of what this is. It's really small. It's a very small piece of it. So if you put the decimal point and all the zeros in front of it, you would see that this is just a really, really small amount of this. It's a very small percentage. So current's flowing down. Some of it goes this way. Some of it goes on down this way. Some of it goes through here. I go through this 25 k ohm resistors, and then it ends up joining up with another current and it goes to ground. So part of this current flows over here. The majority of this current, where it's going is, we're going to come this way, we're going to go this way. We are going to go through, as we can see here, we're going to go through, the majority of it is going to go through the termination. And I've got it modeled as 60 ohms. If this were 120, we'd have half of it going one way, half the other way, and it would join back up. But for us, for what we care about a model, it's the same, doesn't matter. So I've got here 35.61 here, 35.61 here. Has to be. I've got to have the same current. There's nowhere else for it to go. So whatever the current is here, it has to be the same here. These currents then join back up, and amazingly, this is the same amount of current over here, comes back over. Some of the current does flow through the other device, the other CAN transceiver. So this is something else to keep in mind. The more devices I put out here that are in parallel, the more current that whenever somebody's forcing a dominant bit, the more current they have to source, right? So 47 milliamps went here. That's not much current, but if I had 20 or 30 devices here, take that and multiply it by 30 or 20 or 30, and that's a lot of current. We're actually starting to load this bus down. It's more current than we might be able to source with this. So we've got to be careful. That's one of the reasons we don't want too many devices. It's the same thing as putting a bunch of light bulbs on a truck or something, or the tractor. You put a bunch of lights there, everything's going in parallel. Eventually you're going to blow a fuse, right? Because you've put too many lights. People who use LED lights now, it's probably not applicable, but back in the days of incandescent lights, you couldn't put so many lights. Eventually you're going to blow a fuse or pop a circuit breaker, right? Because you just keep increasing that amount of current, each one of these. So we can see some of this current is flowing down here. None of it, absolutely none of it, flies over here to the 2.5 volts, because this point is held at 2.5 volts. It has to be. You can't get to this because you can't put your meter here, but I'm going to go ahead and throw one here just to show this, because it's kind of like, why is there no current flowing back to there? And the reason is, oops, sorry, I put the wrong device there. Let's get we want instead a voltmeter. So I'm going to get a voltmeter. And I'll put the voltmeter here. And we can see that this is at 2.5 volts. You can't get here. But if I looked at what's on the bus, if I were able to look at it, we'll put this stuff here. If I took my multimeter out and I put it on the CAN bus now, we know that this is going to be what, 3.5 something. The other side is going to be 1.5 something or 1.6, right? So put this on there, put that on there. Whoops, got to make it touch. I got a bad connection on my meter here. There we go. Just like a real one, right? So 1.432 volts. We can see right here, this is 2.5 volts. You cannot put your meter here because this is inside of this device. But because this is a parallel circuit, at this point, this has to be with respect to ground. This has to be 2.5 volts. If this is 2.5 volts, this has to be 2.5 volts. You can see I'm showing some current flowing now, and the reason I'm flowing the current is because of, as I said before, let's take that guy out of there. Let's get rid of him and put it back the way he was. Oh no, I got a femto amp. This is something with the simulation of femto, nanopico, femto. Femto is 12th, the 15th. 10 to the negative 15th power. This is basically some rounding error. This is as close to zero as you can probably get. So a femto amp is non-existent. We're going to say that this is zero. Sorry, this is some of the things with simulation that you just kind of have to put up with. It's not perfect. I could probably run the DC simulation again and it'll be back. Nope. Great. That's fantastic. So I do have a femto amp of current that's flowing there that wasn't there before. We'll let that slide. So please don't let that through. So this is zero. So if I think of this, I really have 0 amps that's going from here to here. So no current is virtually flowing. Probably messed that all up for you, but sorry. So I guess the point that I wanted to make here was to show that when you're driving something, the reason that I can have this still be held at 2.5 volts, which may be confusing. Why can this point still be 2.5 volts? It's because I can't access this. This is still allowed to be at the recessive state. So just as soon as I open these switches, I'll open both of them. Just as soon as I open these switches, now we're back to a nano amp. I got a couple of meters here. That's why I got my meters in place. Let's get rid of those. As soon as I get rid of those guys, there we go to 0. Great. As soon as I open those switches again, everybody goes back. Everybody returns to 2.5 volts, right? If I put my meters back in place, I could see that this is 2.5 volts with respect to ground. And of course, as soon as I put my meter back in place, I'm going to see some current because back to the Heisenberg uncertainty principle, if I look at it, I change it. And that's what I've done here. I'm observing it. I'm testing something with it. And so I've changed the circuit slightly, ever so slightly. But anyways, this is the concept I guess I wanted to get across here, this idea of I have to drive it to get it to the dominant state. So I have to have both of these switches closed. Please don't look at it with one closed. That's bad. When I have both switches closed, we can see that I've driven the data link to high. I can still have this point. This guy can still be 2.5 volts. And the reason it can be 2.5 volts is because there's no current that's flowing here. This point is held at 2.5 volts. If I got really creative, I could take a meter, and if I were inside of this and I'm like, okay, I want to see, what that is. Well, I can use this floating multimeter here. We can take it over and we can say, yes, it's 1.068 volts. And you see, I just changed some current there. I could do the same thing with the other side. We'll take a look at it and what it does. And there we go. Our voltage is, these are positive together, 1.068 volts. And there's this magic law that says basically if I add up all the voltage drops, they have to equal whatever this resulting voltage that I would measure on all these would be the sum of these. So if I look at this, this is 2.136, 1.068, 1.068. Probably more confusing than it is helpful. But if you had stuck in your mind, how can I be driving this to one value and still have this 2.5 volt supply be there? This is the reason why. If you look at this long enough, hopefully it'll make sense. Once again, I'm back to some microvolts, really, really small voltage, just because of the meters themselves. I'm flowing some current through the meter, so I've got a voltage drop, or I've got a resistance of the meter. So because it's a real, or simulating a real meter, it shows this thing of voltage. So hopefully this will make sense. If it doesn't, I'll probably just delete this one, and I'll move on to something else. So let me know, did this help or hurt you? I would appreciate in the comments. Thanks.